Okay, so it gives me great pleasure to introduce Kartik, who's going to talk about his master's paper work on quantum Hoare type theory. So please take it away.
Thanks, John. Hi, everyone. Thanks for coming to my talk. As we know, quantum computing is famously difficult to understand, but the machines are coming. And we know from last year that Google announced this breakthrough result called, where they demonstrated quantum supremacy, which means at a point in time when quantum machines demonstrably can perform a computation which a classical supercomputer cannot. And as recently as last week, another group from China announced even bigger breakthrough where they claim to have done a computation on a boson sampling problem on a quantum computer where they can perform a computation which will take a classical supercomputer like about more than 500 million years to perform. So this is a point where we really need to start thinking seriously about quantum machines and the software for them. So the question is, what do we computer scientists, what can we do about this? In my research, I have this long-term vision for computing, which is inspired by something my undergrad advisor used to say. So it goes something like, while a civil engineer as a profession provides specific guarantees and about the efficacy and failure modes of a bridge that they design, a software engineer for a software product does not. In fact, we are sort of infamous, when we publish software, we say that it doesn't come with any warranties, etc. So he goes on to say that computing as a scientific discipline has come a long way, but as an engineering discipline, it has miles to go. If we think about the past 70 years of classical computing, we haven't really achieved this goal of this utopian goal of being able to provide solid guarantees about software. But we are currently in the 60s era of quantum computing. The machines are just coming up, and it gives us a unique opportunity to think about how we want to design software in future in a principled manner. So let me motivate a little more by, let me describe what approaches people generally take in, classical in classical computing for writing reliable software. And I really like this slide from Professor Benjamin Pierce of UPenn, who's also written a series of textbooks for writing reliable software. So there's a whole spectrum of approaches people take while writing correct software. They range from being social, where everybody's familiar with code reviews or pair programming, and then there are methodological approaches, such as using certain design patterns, doing test-driven development, or version control using tools like Git, then issue tracking, and then people use static tools like linters and random testing. And then there are mathematical tools such as using sound type systems and formal verification. So they are on a spectrum because partly because some of them are easier to use, but the trade-off is that they may not guarantee a lot about, they may not say a lot about the correctness of your software. And some are quite formal and they can with certainty eliminate as many bugs and problems as possible. But Benjamin warns that this isn't a trade-off. We should be using all of these methods. Plus, there's a quip from Donald Knuth that beware of bugs in the above code. I've only proved it correct and not tried it. So even with these bottom approaches, which is what my research focuses on, it's not a silver bullet. So we should be cognizant that whatever I present here should be used along with whatever approach I'm proposing here should also be used with, complemented with other techniques presented here. So now let's try to motivate why do we need reliable quantum software. So one of the main, there are a couple of problems in trying to directly adopt the techniques from classical computing. One of the most prominent one is that quantum computing, and I know I have not really introduced any background on quantum computing yet, but it's generally known that when you measure a quantum state, it collapses. So you lose some information in the process of measurement, and that is important when you're trying to do any computation. Other reason is like in classical computing, people generally just run the code and see what happens to understand it and to debug it. So this approach works for a small number of qubits in quantum computing case, but it's not really scalable because, as we'll see, the fundamentally quantum computing is different because it can represent a huge amount of state, which can be exponential compared to classical bits. So we run into issues of running out of memory when we try to simulate quantum machines on a classical computer. Other reason is that currently quantum machines, even if you are at Google or at IBM, you have these machines, the cost is still pretty high to run your software. Some of us may be aware that just setting up an initial stable state on a quantum computer, depending on the architecture, can sometimes take days. And even if you are willing to wait for that, the cost of running incorrect software is even worse. So you really do not want to do that. So ideally, we would like to eliminate as many problems as possible before running the program. And that's what I mean by statically here. So in this work, our approach is to adapt the best classical static typing techniques and apply them into the quantum realm, while keeping in mind that we want to enable the programmers to use those techniques and not needing to learn a lot about formal verification or very mathematical approaches. So this work, as a side goal, tries to adopt techniques that are directly helpful to programmers. And I would like to mention that initial part of this work was presented at QPL earlier this year in June. And the work I'm presenting is an extension of that. And we have some interesting proofs that I can show you today. So here is a general overview of the talk. I'll spend a bunch of time explaining some background on, especially on Floyd-Hoare logic, and maybe not as much time on the remaining background topics. Then I will move on to Quantum Hoare Type Theory, which sort of combines the ideas from existing techniques into a single unified whole. And I'll share the rules for primitive commands for quantum computing that we introduce in this work. And the main example will be showing verification for teleportation. Finally, I'll recap and suggest a lot of interesting future directions. I mean, this work is nowhere near the idea we would like to achieve if we want to enable programmers, really. In terms of questions, so I'll be taking breaks after each of these sections, after classical background, quantum background, etc. But if there are any clarification questions, please feel free to interrupt me, either raise your hand or just speak up, and I'll be happy to respond right away. Let me move this participant screen up. Okay. So before I get started, any questions so far? Okay. If not, let's move on. Okay. So let's talk about Floyd-Hoare logic. It's a technique that was really established in or introduced in late 60s by Bob Floyd and Tony Hoare. Floyd had applied it to flowchart languages, and Tony Hoare did it for textual programs. So it is also just known as Hoare-logic. It has been proven to be quite effectful in reasoning about state manipulating imperative programs in the classical setting. So the core concept in Hoare logic is of a Hoare triple, which in its general form looks like this. where P and Q are pre and post conditions on the state of the program, and C is the program to be executed. So these P and Q could be arbitrary logical statements about the program state, and I will see some examples soon. So the way to read this triple is that if P, the precondition P is true before the execution of the command C, then Q will be true on its completion. And here's a simple example where the command is an assignment command where variable X is being assigned the value 5, and there are some arbitrary pre and post conditions on it. So initially X was 1, and later the user has said that X is greater than 0. So you will notice that these are not very interesting pre and post conditions, and I've intentionally shown these because we want to be able to support whatever the user wants in these pre and post conditions as long as they are valid. And if you think about it, the precondition on this program does not really matter. It could have been just true because whatever X would be will be reassigned to 5 after execution of this command. And in the post condition, the most precise or strongest post condition you can find is X equal to 5. So so let's look at how reasoning proceeds in these systems. So there are certain axioms and rules of inference defined for reasoning in Hoare-logic. So is a axiom for assignment where we have the general command X equal to some expression E, and it is given a post condition P. So this axiom says that to derive a precondition, we take the post condition P and substitute any occurrences of the variable X by the expression E. And this is just an axiom that gives you the weakest precondition for the assignment statement. And I'll show an example in the next slide. So then let's look at a rule. So this rule of consequence, the way to read this kind of rule is the things above the bar are called premises and the bottom thing is called a conclusion. So what this rule is saying is that if you have a triple QCR, and if there is some proposition P, if that implies Q, then we can replace this precondition with P. So this technique of strengthening the precondition can also be written as a separate rule of its own. I've just combined them here, and it's called precondition strengthening. In the other direction, we can weaken the post condition. So we had R here, and if R implies some other proposition S, we can just replace it with S. So I'll not show an example of this right now, but this is the rule which helps us reason about the triple that we saw in the previous slide, where the user can give us arbitrary triples, and we figure out what is the weakest precondition or the strongest post condition, and figure out whether they imply each other or not, respectively. So moving on, another very interesting and useful rule is this rule of composition, also called rule of sequencing, where you have two commands C and D. They individually have these triples around them. And notice that the post condition Q here is the same as the precondition D here. So if that's the case, we can reason about the sequence of composition of these two programs like this. You can use the precondition on the first command as the precondition of the whole program, and the post condition of the second command as the post condition of the whole program. And now let's look at an example. Here is the typical program that most of us may have written to swap two variables. So we have a temporary variable t. We store the value of x in it, then rewrite x, and then assign rewrite x with y, and then y can be given that temporary value. So the pre and post conditions here are as what you would expect in a swap program, that initially x is some m, y is some n, and this end is the logical conjunction operator. And in the post condition, you would want these values swapped. So y becomes m and x is equal to m. So what we can do is we can use the assignment axiom and the composition rule that we saw above in the previous slide to proceed in the backward direction. So notice that we have only two commands remaining here. So what has happened is this change. We look at this last command using the composition rule. We figure out its weakest precondition by using the assignment axiom. And what that says is whatever the value of y, y is being assigned t, so t will become the value of y, and you substitute it in the post condition that was there after this command. So this is what we have done. We have replaced y with t in this triple. And now we can eliminate this command and just look at the remaining program. Moving similarly, we can take another step where we replace the value of x in this triple with the value y. So now notice that we are left with just a single assignment, and this is very close to what we want. So y is equal to n, which is what we want. And if we take one more step in the same direction, we'll achieve the same precondition. So this shows how reasoning proceeds in a system like Hoare-logic. And we've been using these M and N, and we noticed that they are not really part of the program. So in Hoare-logic, the idea of these variables that are only used in the specification in the triples is they are called ghost variables. Another term is logical variables, or you can also call them auxiliary variables, but we'll use the terminology ghost variables for this work. So there's something unsatisfying about this way of proof. So we mentioned we really like types, and we can, so types are completely missing here, right? We do not know what the value type of x is, what the value of t, what the type of t is, because types help us eliminate bugs. We would like this, Hoare-logic kind of reasoning to appear in a setting of types. So this is where Hoare type theory comes in, which combines the power of Hoare-logic with something called dependent types, which are able to express a lot. So let's look at, before I go there, so this work on Hoare type theory was done in late 2000s primarily led by Alex Nanevsky and his group. So, so let's look at say a Hoare triple, but written as a Hoare type. So Hoare types they look generally in the form like this, where pre and post conditions are specified in the type itself. And these can be very expressive because they are dependent types. So what we are seeing here is the pre and post conditions P and Q, same as before. The middle part is different this time. Instead of the program itself or the command, we write the name of the output here, x, and along with its type. So x colon a is the representation of a variable and a variable. So this is the form we'll use in a Hoare type. And finally, there's a context attached sometimes in the Hoare type to bind ghost variables that we saw before. And here is an example of the swap function that we saw before. So this is directly taken from Nanevsky's work. And this example kind of also shows you how expressive these types can be. They are using, I'll describe some of these things in detail, but the idea is that you can say a lot about your programs using Hoare types. So what this says is, for any type alpha and beta, so we see polymorphism appear here. This is a function. So pi is a dependent function binder from dependent types. So this is a function because it starts with a pi. It takes two variables, x and y, as input, which are locations. They are modeled as natural numbers in this example. And then it returns this output, which is a Hoare type in its complete form. So here M and N are logical variables or ghost variables. They are of these types, alpha and beta, so they are polymorphic. And then we see the triple, the precondition in the triple where X is initially M, Y is initially N, and in the postcondition X becomes N and Y becomes M. And we are using this equal alpha symbol just to distinguish between different types of equalities. So it does not really matter here. And notice the output type here is unit, because the swap command does not really return any output. It swaps the values in place. So we do not expect anything interesting to come out. We just type it as unit. And this interesting star symbol that we see here, this is probably not relevant for this talk, but it is something called separating conjunction, and it's quite powerful. It's quite a powerful technique from separation logic used in reasoning about classical state manipulating programs. So last slide before this section finishes. We'll be using a different syntax in this work, inspired by this programming language called F-star, which is work by Nick Swamy et al. And from 2016 onwards and still ongoing, which is an evolution of a system like Hoare type theory. So we saw our initial example, which had these weird pre and post conditions. We can write it as a Hoare type. So where the left side is the program, colon just specifies that right side of the colon is the type, and this is the type, which is similar to the Hoare triple we saw. So the way we will write this in F-star is using, by annotating it with the kind of effect it has. So in case of classical programs, people familiar with Haskell may recognize this ST. So in F-star, ST is called an effect, where we are saying that type of computation that this program does is of state, changing the state. So the way we write this in F-star is program same as before. We annotate with the type effect type ST. The output appears first, so R being the name of the variable, unit the type, and then pre and post conditions are annotated by these keywords requires and ensures. So the reason we want to use this is just because it brings a lot of readability to the Hoare type. So you don't necessarily have to know what these braces mean. And we'll be using this in this work, this syntax in this work, and we will annotate our quantum Hoare types with this effect QST. So now I'll be happy to take any questions related to the portion so far. Okay, if not, let's move on. So let's talk about quantum computation. And it's a tough task to summarize quantum mechanics and quantum computation in a single slide, but I'll try to do that. So it's generally, first of all, in early 80s, Richard Feynman came up with this idea that the nature is quantum mechanical, so we ought to be able to build computers using quantum mechanics, and that's kind of where how the field of quantum computation started. So now what our goal is to be able to reason about quantum computation. So what we would like to do is first try to understand what the basic four postulates of quantum mechanics. And the core idea to understand is that most of, or rather mathematically, all of quantum mechanics can be described using linear algebra. And so first postulate of quantum mechanics describes how do you specify the state. And what that says is that states in quantum mechanics are just unit vectors in a complex vector space, written here as Cn, where n is the dimension of the space. And it's commonly also known as Hilbert space, but for our needs in a finite dimensional Hilbert space, we can just think of it as a complex vector space. And examples that I'll show on the right will be pertaining to C squared, that is a complex vector space of dimension 2. So here are the basis vectors in that. And this notation is called bracket notation. So the way I can read this as ket0, which is a column vector 1, 0. And similarly, for the other vector 1, ket1, we have 0, 1. So these are also known as computational basis vectors. And we'll see that term again. So just to introduce it here. Then a general arbitrary state vector in a two-dimensional space can be written as alpha ket0 plus beta ket1. And this is the simple psi. So, and this linear combination of vectors is also known as superposition. In the context of quantum computation, we'll often hear this term. And then there's a normalization condition on these alpha and beta scalars, which are complex numbers, that they should, sum of their squares should sum up to 1. And this is where this unit vector notion comes in. So this is just a constraint on how vectors are allowed, what vectors are allowed in the state space. This animation appeared early, but the second postulate says that to do any computation in this, a system, quantum system, what we do is we apply unitary matrices that will change the state somehow. So here is an example of a very simple matrix called X or not, which looks like this. It's just a 2 by 2 matrix, and
it's
we multiply this by the state vector given above. And what it does is it swaps the two vectors. So, or we can think of it as swapping the amplitude. So alpha 1 and beta 0 instead of 0 and 1 we saw above. Then there is another, so I should mention that these two first postulates are about isolated systems. And the third postulate describes what if we as an external observer want to get information out of the system. So that is something called measurement. And I'll not describe too much in detail what that does, but the idea is that it says how the final outputs when you measure a vector like this correspond to with what probabilities you get them. So alpha square that we see here is the probability of getting the output 0, and beta square is 1. And I'll be using a little bit of circuit notation, and just to see this in future slides, this is the notation used for a measurement gate. And I'll show some more gates on the next slide. And finally, the last postulate tells us how do we combine multiple such quantum systems. So for that, we take the tensor product operation on the spaces, and it can be written using this O time symbol, and we'll be seeing this more. In terms of this work, we will look at all these things in terms of some primitive commands where you can initialize, you can take a bit and initialize it to a qubit. So this will be in the form initHam. You can apply unitary operations to a given qubit. That will be the apply command, and then you can measure certain qubits. So we'll be using MES for that. So moving on, here are some common gates. There's a, like we saw X, there is a Z gate, which is very simple. It basically inverts the phase, and I'll not describe phase right now, but this is the matrix representation of that. Very commonly used gate is called Hadamard, which we will be using in examples. What it does is it puts a given qubit into a superposition, eco-superposition of its initial state, especially if it's a 0 qubit. Then there is an idea of controlled gates. So here are two examples. Like Z, you can conditionally apply certain gates so first of all, we'll notice that these matrices are bigger, 4 by 4 instead of 2 by 2. So the idea is that they are operating on 2 qubits at a time. And where in this notation, this darkened dot means that first one is a control. That is, if it is 1, only then the bottom gate that we see will be applied to the second qubit. And control not is special that it has this common notation, but we can also use this notation for that. So these matrices are not important right now, but so let's move on. So we looked at Hoare-logic in the classical sense, and there is also similar work in quantum setting in the last 10, 12 years. I'll be specifically describing some of the background on quantum Hoare-logic by Dominic Unruh, who also uses ghost variables in his work. But the general notion behind a lot of these quantum Hoare-logics comes from a very old idea from Birkhoff and von Neumann from 1936, where it's established that subspaces of a state space can be thought of as logical propositions. So that's what most of these logics build upon. And in our case, Unruh's QHL describes some interesting predicates we'll be using. So here is top, just an SST. It's always true, like we talked about in the beginning, and it kind of represents the complete space under consideration. Then you can take a conjunction of two propositions, which is equivalent to the intersection of two subspaces. Then there is this U dot P, which is basically, it represents the state obtained after applying U to all the states in a subspace P. So this is something we'll use when we apply unitary gates. And then a very, very useful predicate is where you can say what state does a set of variables X hold. So all of these predicates that we are seeing have some meaning in the subspaces sense as well. And for reasons of conciseness, I'm not introducing everything, but it's in the paper. And then there's the notion of quantum equality, that you can take two quantum variables which are disjoint and say whether they are equal or not. I mean, they're equal here. And similarly, another notion is of classical equality between two variables, where what this means is that if you were to measure X in the computational basis and Y in the computational basis, you will always get the same results. So that's sort of the intuition behind classical equality. Now, there's another part of Unruh's work which is very useful to us, and that's the notion of ghost variables he introduces, which are specific to quantum computing. So there are primarily two different ghost variables he introduces. One is called entangled ghost variable, and it's denoted by E. Similarly, there's U for unentangled ghost variables. So what they let us do is talk about certain properties in the specification, which using some qubits, and we'll see examples when I walk through our proofs. And another way these ghost variables are used is by defining more predicates apart from those we saw in the previous slide. So one is separable, which takes a variable or list of variables as input, and the way it is defined is that these variables X are quantumly equal to some unentangled ghost U, which would make sense because separable states are those which can be talked about without considering other parts of the quantum state. So U basically denotes separable quantum state. So X quantumly equal to U can be written as separable X then. Similarly, another useful predicate is class X, where X is the given variable X or list of variables X is classically equal to E to some entangled variable in the system, where on measurement, they will return same outputs. So just to show that this is a Hoare logic, I wanted to show just a couple rules in this, or axioms in this logic. So here is the axiom for unitary application. So the command we saw, apply U to X. This is from Unruh's work, where if you're given a proposition P, the post condition for this command just becomes u on x dot p. So this notation basically means that u may be applied to only a part of the subspace which is represented by x, and we saw this u dot p predicate in the previous slide. So this lets us do forward reasoning on application of unitaries. And again, we'll be directly using this rule in our work. And then there's another axiom, which is a little more interesting, but we will not be using it, where there is initialization of some qubit being done. Here, x is supposed to be a qubit, which is different from the language I'll show you later. But the idea is that given some proposition P, the postconditions or strongest postcondition in Unruh's quantum Hoare logic is that you replace all occurrences of this X in the precondition P by an entangled ghost E. So Unruh's init basically discards the previous state by changing it by a ghost or replacing it by a ghost variable. And then you bind a new variable x with the initial state 0 in the system, and basically you add it to the system. This is just to show that these entangled ghost variables can be used in the axioms or rules of the logic. So this closes the background on quantum section of this talk as well. And if there are any questions, I would love to hear them.
Yeah, Kartik, I have a question.
Yes.
Can you tell me again what separable X means? I wasn't sure I got that.
So in certain situations, we want to be able to state that a given qubit or maybe a bunch of qubits are not entangled. So this predicate separable lets us specify that in our specification language.
Yeah, so I understand what a separable quantum state is, but usually when you say something is separable in quantum information, you also have to specify some partition of the Hilbert space. You have to say something like, the first 5 qubits are unentangled with the second 5 qubits or something like that. So I don't know exactly what you mean when you just say separable state.
I see. Yeah, I think this is part of the technicalities of the ghost variables that I did not mention. I'll show the example or one of our rules where this will become clear. But when we see the use of a ghost variable in Unruh's work, that basically means this ghost variable can take any value that is needed to make the given predicate true. Okay. So in this case, all it is saying is that if you are given a bunch of qubits represented by this capital X, they are in some unentangled or some state which is represented by U, which is separable, like not, we don't need to specify the partition because that's just out of consideration right now.
Okay. I mean, is it important that that like separable X is like efficiently computable? That like if I give you a state, I can tell you, there's an algorithm to tell you if it's separable or not?
I believe not in general, but we have also not investigated that.
Okay, because that could be an issue here, because in general, there's no such algorithm. This is like an NP-hard problem, depending on how you formulate it. So I'm just curious to know how important it is if you can actually check if a state is separable or not in this context.
Right. I believe, yeah, that's definitely a consideration, and at least the examples I've worked through, that does not. Is not required to figure out whether something is separable. We only specify it and check whether given propositions can imply that something is separable or not. And I think it will become clear with the examples as well.
Okay, thanks.
And I think John has his hand raised.
Yeah. So my question has to do about notation here. So for initialization, you have this notation P with X, open square bracket, X arrow E, close square bracket, which imply, so reads like it's, update, think of P as some kind of finite map and update it the definition of X to be E. But of
Yeah.
course, E is not a finite map. P is a subspace of this Hilbert space. So what does this notation mean in terms of subspaces?
Well, the idea of this substitution only applies to term language, and P in that scenario is just whatever textual propositions we have given. So I mean, we can think about how to think of this in subspaces, but this rule does not talk about subspaces. This applies it symbolically on the term language of the proposition.
So then the P, that P is different than the P on the previous page where you talked about vectors being elements of P, like when you have U dot P.
Okay, so the P's that we see here, or the atomic P's, are top and state equality, and potentially these quantum and classical equalities. So really, I mean, they are defined in terms of these atomic propositions, but their semantic meaning comes from this idea that semantically they are equivalent to some subspaces. Like, I did not say it in this slide, but this state equality predicate says that X is in the span of this vector psi. So which becomes a subspace on its own. So
you're essentially punning that you're using the syntactic form of these predicates as to also stand for the sort of semantic subspaces that model them.
Yeah, I think that's fair to say.
And you're just going back and forth based on convenience.
Yeah, maybe that's probably a fair characterization in this case.
All right. Well,
Kartik, I wanted to follow up on Bill's question on the next slide. So the X's for classical or for separable or classic or class as well can be some collection of qubits, correct?
Yes.
And when we say separable X, we're saying that this collection of qubits is separable not from one another, but from the rest of the system, correct?
Right. Yeah.
Okay, so that's just one thing to be clear. We're not trying to divide within the system. And I'm guessing you would generally say separable if, for instance, like you initialized a new qubit, then you should always be able to derive that it's separable from the rest of the qubits simply because it's been
separable
initialized.
is a weaker assertion or very weaker proposition on the same state. The strongest is that this is the exact state that we know of a particular qubit when we initialize it. So, for example, this. And with
sure, but
yeah.
So just in terms of deciding separability, it's more that you would want to track separability through your program because you know what the qubit initialized at, and maybe it's never entangled with anything. Then you want some decidable algorithm for determining separability once you already have a highly entangled state.
Yeah, I would agree with that. Yeah.
Yeah, thanks, Robert. That makes a lot more sense.
All right.
Sorry, I have one more question, Kartik. Can you tell me what do you mean by quantum equality? Did you define that? I'm not sure I understand that.
So so the way so this is basically from Unru's work. The way it is defined, and thanks for pointing out that I actually did not say anything more about what this means. At an intuitive level, and I know it's somewhat subtle to define precisely, but at an intuitive level, what this means is that X and Y are a set of qubits each, of course, of the same number and dimension, which given a quantum system, if you replace the set of qubits X with set of qubits Y, nothing will change. That is, they are equal in all possible senses of the word equal, except their names.
But, but I think it's okay. There's a few things I would say about that. The first thing is that if you define it that strictly, then again, you're going to have algorithmic problems in terms of like trying to check equality. There's not going to be like an efficient algorithm for that. And then the second thing is that, there's not going to be a quantum algorithm for that either, by the way. So my guess is that what you actually want to make it a little bit more feasible is some sort of approximate equality. And there's many norms in which you can define that, for say 2 quantum states. I'm just wondering if some of your results, whatever you're going to show us, would sort of hold just as well if I gave you some norm and I told you that these, with respect to some norm, these 2 quantum states are epsilon close or something like that.
I see. Yeah, that's not something we have considered so far, but it's I might discuss that in future work. I mean,
Okay.
we've been thinking about resource theories, so I don't know if that's something close to norms that you're talking about, but we have been thinking about.
No, it's probably different, but we can talk about it later.
Okay.
So I'd really like to just jump in here. I don't think one normally needs to compute equality in these things. It's kind of a specification. I mean,
Okay.
in a lot of these reasoning systems, equality, for example, people often reason about equality of functions, which is completely undecidable. But
Yeah.
you can make an assertion that if f is equal to g, then certain properties follow from that assumption. And so, it's not necessarily going to be something that one actually has to be able to compute. It's rather something that is useful from the point of view of being able to specify properties of the algorithm that you're reasoning about.
Okay, thanks. That makes a lot of sense.
Yeah, thanks, Sean. Okay, let's move on. And I see that I'm a little behind time, so I'll try to be mindful of time and introduce the rest of the work. So this brings us to quantum Hoare type theory, where as we saw in the classical setting, we can take a Hoare type and index it with the type of the result that a quantum computation will give us, and also its pre and post conditions. So we get a quantum Hoare type. The main difference is obviously it's in the name, it's quantum. So instead of reasoning about classical heaps or state, we will be reasoning about quantum state here. And then the primitive commands that manipulate that state are different. And I'll introduce that in the next slides. And from Unruh's QHL, our rules are somewhat simpler. And I would be glad, I should definitely say that they are also simpler because we have tried less number of examples so far. But they're also presented in a type theoretical setting. So they have the advantage of, being able to easily mechanize into dependent type theories. So let's look at our first primitive command called initialization, where in this, our restricted language, we only can initialize a qubit at a time in only the basis state 0, 1. So here is a Hoare type for the init_m command, which is a function, and it takes a bit b and it returns a qubit q. And I've annotated it with its effect type QST, as we've discussed before. So the requirement on this command is nothing. It's always going to be true that that means you can initialize a qubit whenever you want. And this is under the assumption that you have a countably infinite set of qubits available, logical qubits. And then what it ensures is also pretty simple. It just says that the given qubit q will be in the state ket b, either 0 or 1. So it will be ket 0 or ket 1. And one thing I should mention is that our presentation of these rules is in some sense in something called frame rules, that we are presenting them in a way that we don't care about the rest of the state. And when we do, we will specify that. So this rule can be used wherever, and it will basically just add another proposition to the given set of propositions when you initialize a qubit. And we'll see an example later. And this is a simple example that, doing init 0 gives you ket 0, so I'll skip that. Next comes the measurement rule, which is a little more interesting. our assumption is they're always in the computational basis, that is ket 0 or ket 1. And the rule goes like this. It obviously takes a qubit as input and it returns a bit as output. Again, the type or effect type QST. Now, this is something new here, and this is the context we showed delta for binding ghost variables. So we have a psi, which is a vector, and a ghost variable EX, which is a of type qubit. So what the precondition here says that in whatever context in subsystem H is representing Hilbert space, so the complete state under consideration. So let's read the right part first. This is saying that if the overall system is in the state psi, and here's sort of a partition we are considering, where Q is considered separately from the rest of the system by this notation, where we are saying if V is the set of all qubits, we remove Q and take the state space associated to that. If that is psi, in the post condition, we will replace this Q with the entangled ghost variable, and the state will remain the same. So what this lets us do is maintain the outcome distribution of whatever Q could have been. So we can think of EX as the ghost of the measured qubit Q. And then we can we also assign this post condition sort of one proposition on Q that this is now a qubit which is in the classical state. In terms of its semantics, so we can think of it as discarded. That is, since it's in classical state and we don't have a reference to it, we will not be able to do any operations on Q anymore. But we do have a, we can refer it in the logical specification. And this I already mentioned, we are able to say that the distribution of the outcome is maintained. And like I talked about frame rules before, this is only considering the subsystem under consideration. So in Hoare-logic terminology, it can be called local state, or rather Hoare type theory terminology. And then finally is the unitary application rule, which is not very insightful because it's the same as what we saw before in Unruh's work, where we can apply some, I'm calling it G, but it's a unitary, to some qubits Qs. And whatever the proposition on, this is a ghost proposition now, whatever it was, we will just apply G on QS in P. So basically directly using what Unruh does. And it's helpful to think of it in terms of two different types because we only currently support single and 2 qubit gates. So, it either takes a single qubit and a single qubit unitary, or it takes a pair of qubits and returns the same kind of propositions. And I've omitted those here. So this brings us to our first example of creating a Bell state. I'll show a circuit first, because some people may be familiar with this notation. What it's doing is it takes 2 qubits. The circuit takes 2 qubits, which are initially in state 0, applies the Hadamard gate, and then applies the control knot CX gate, and then it returns our first Bell pair state, which can be written out more precisely as this, which is the common amplitude 1/√2, and the states are 0, 0, and 1, 1. What this means is that the 2 qubits that were given are in maximally entangled state. They could either be both 0, 0 or both 1, 1, since the probability amplitude here is 1/√2, which gives you half and half for each of these states. So we can write this in code as follows. The type would be, we are not requiring any input because we will initialize new qubits. It returns a pair of qubits as output, and requirement here is nothing. It can be run in any context possible. So we just say true or top. And then the post condition is the most precise possible, where AB is returned in the beta 00, ket B, beta 00 state. So here's the program in that language we saw. So we initialize a qubit to 0, then apply Hadamard. So this is the translation of this circuit in the code. And then finally, after applying these gates, we can return it. So let's quickly step through what the verification looks like in this case. So we said the precondition is stop, so that is assumed here. When you initialize it, the set of propositions now include a precise A equal to ket0 state proposition. Applying Hadamard, we can use the axiom for applying unitaries, and I'm using this symbol to just show rewriting or a simplification step. So now we know that A is in this precise ket plus state, which is the equal superposition of 0 and 1. And that's the job of the Hadamard gate. Then we initialize another qubit that gets added to the propositions. So beta equal to 0 here, B equal to 0, ket 0. And then like we did above, we apply the CX gate on the previous proposition, which was this, which can be further simplified to exactly the state. And return does not really do anything special in this case because we have the right postcondition we wanted. Now, quantum teleportation is another interesting example that we were able to prove. Is it the circuit in the circuit, the teleportation algorithm?
It's 2 o'clock.
Protocol in the circuit form where there's an arbitrary state psi, and there is a pair of qubit in the beta 00 state that we saw before. And what this algorithm does is it transmits or transports the state which was given to the first qubit to the final qubit. And it consumes the entangled qubit pair that was given during the process. So there's a fundamental negative law in quantum mechanics that you cannot clone states, but this protocol basically lets you copy a qubit. So let's see how this looks like in our system. So here we are taking a qubit as input, and then we are returning another qubit as output. The ghost variable is a vector psi, which is an arbitrary state. So we can say that Q is initially in psi, in this Q being the input. And in the postcondition, we are saying that Q that was given to us will be collapsed. It will become classical. And then the returned qubit will have the psi state. So this class Q postcondition is important here and maybe relevant here, because otherwise you could be just, at least in symbolically, you could be just returning the given qubit Q directly as output and renaming it to B. So we don't want to allow that. So here's the code. And a couple interesting things here. We are able to use the Bell 00 function we defined in the previous slide to initialize 2 qubits AB to the Bell pair. Then we just apply these gates, CX and H. And then the new thing here is that we are doing some measurements on the first 2 qubits. And then we are applying these CX CZ gates to the controlled by the classical bits obtained, X and Y. So fine, let's look at how verification proceeds in this example. And I know this looks very hairy, so you don't have to read all of the code I'm showing here. So I'll just point out things that are useful. So first of all, we said that the requirement was that Q should be psi. So we take that. And since it was arbitrary, we can write it in this form, alpha 0 plus beta n. So an arbitrary single qubit state. Now, on a function call, the postcondition of Bell 00 was just AP equal to ket beta 00. So that can be appended here. And again, there's a rewriting step involved that we can do. So sort of doing the tensor product of these 2 vectors and getting a symbolic representation of the complete system, complete state. Now, the application of CX and H are as usual as before. They will be applied and these symbols will change accordingly. So let's look at the next interesting thing here, which is measurement. So as we saw, the rule for measurement involves replacing the qubit that is being measured with the entangled ghost variable. So here it's called EX, and also assigning a class predicate on the given qubit Q. And there's a reason why we use this EX sub X notation, because we do want to, since we said this EX is going to carry the outcome distribution of the measured qubit, we will be able to use it to tie it with what X was after measurement. So we proceed similarly in case of the Y as well. So we get another proposition here, and A gets replaced with EY. Nothing else changes really. And then moving on, so up to this is the same as previous slide, 26 line. Then another interesting thing is when we are applying this CX gate at using the given bit Y and the qubit B. So now, as we saw in the previous proposition, that we had some hold of the state that Y could take. So this basically means that we can apply the CX operation looking at to this state, which includes the ghost variable. So all the manipulations I've done here are the same as you would do in a textbook proof or handwritten proof, but we are able to tie this together with the bit Y because we have a corresponding ghost qubit here. And moving in the similar direction, we can do that for CZ. And finally, what we obtain is, after a simplification step, this is probably related to Bill's question earlier. Like we want to be able to say that EX, EY form a separate state of their own and B is separable now. But after simplification, we obtain the original state psi that we had seen. So now we had more assertions here. We had class A, but the postcondition only requires that postcondition in the actual original program doesn't say anything about A. So we can weaken the the strongest postcondition obtained here to the one we are seeing at this line. That includes only class Q and B equal to a certain state. So this kind of demonstrates how reasoning follows in the system. And another way we can think about writing teleportation is by breaking it into pieces traditionally presented. The quantum teleportation protocol presented using two actors, Alice and Bob, and we can write their components separately. So here I'm only showing how that concise modular version of teleportation will look like, where we are doing 3 function calls, Bell 00, Alice, and Bob. And the specifications of Alice and Bob are included in their Hoare types. So it does look pretty hairy, but that's kind of is needed to carry the proof through from Alice to Bob in this case here. Yeah, I mean, this specification we are seeing is kind of same as we saw in the middle of the steps in the previous slide. One interesting thing I'll point out here is this, where we are saying that the Q is in some arbitrary state of 0, beta 1, but since Alice works with only a part of the Bell pair, we need a way to specify that somehow. So for that, we use a ghost entangle variable here called E. So this way you can specify that this Alice's code needs a Bell pair. In case of Bob, it only needs 2 bits and a qubit, so we don't need to specify an entangled ghost variable here. We can just work with usual logical variables or ghost variables based on based on their amplitude. So yeah, I mean, I'm happy to talk more about this, but it's doable. And finally, to recap, and I will take questions after this. What we do in this work is we take sort of ideas in classical computing where Hoare-logic has been very effective, and that has been used in Hoare type theory in the setting of types. And then apply them to the quantum setting using some inspiration from quantum Hoare logics or the idea of subspaces as predicates, and then come up with this system called QHTT. And the general hope is that this can be a unified system where you can do both programming and specification of the programs, and also reasoning using, as we saw above. So it's a dependent type theory in which types have can specify pre and post conditions. Then the general idea is that if your type checking goes through, it means that the program you have implemented is correct up to those specifications. And it also comes with this specification language, which lets you specify interesting properties about your program, such as whether a certain state is separable or if it is in classical, and the state predicates that we saw above. So we have other things we have done is we have a Deutsch algorithm proof, which is a little more hairy, but all those details are in the paper and it's currently on arXiv. And yeah, that's all. Maybe I can wait for some questions before I conclude.
So this is all written in terms of like pure states. Have you thought, but of course, like a general quantum system is really a mixed state. Have you thought about sort of whether any of this would sort of carry over to more general cases?
Yeah, that's an interesting question, and I was going to talk about it in the future directions.
Okay.
But indeed, the Unruh system does work in mixed states, and but we wanted to see how much can we achieve with just pure states themselves without needing to, resort to density matrices, because after mixed states we do need to use that representation.
Yeah, I guess it's fine as long as you're considering sort of fault-tolerant quantum systems, which is probably sort of implicit in all of this. Is that right? Okay, cool.
All right, let me talk a little bit about future directions, because this work can actually lead to some very interesting ideas. So one obvious direction is that we mechanize it in a dependent type theory like Coq or F star, which will also enable us to extract higher level programs or modular programs that we saw into a lower level language like CHASM. We currently do not support iterative or recursive constructs, which are common in other higher level languages. So it would be nice to have that. Plus also a very interesting thing is just composing pure unitary operators that do not necessarily, or just the composing unitary operators does not involve states. So incorporating that to construct new operators would be nice. And there is existing work which includes linear types in a dependent type setting by Peter Selinger's group. So this paper came out only early this year at Lakes. So this is a very interesting direction that we should be able to just use linear types to avoid specifying anything about whether a qubit is cloned or not. And similarly, we have joint work with Robert Wren, Aarti Sundaram, and Brad Lackey on using Gottesman types based on the Heisenberg representation, where you can say some things, you can specify types which say something like a certain state is in a certain stabilizer, or it is stabilized by a certain stabilizer. So we have types like Z and X, which are for computational basis state and the Hadamard basis state respectively. And there are more interesting ideas there. Similarly, one other thing that this framework can let us explore is probably other richer types, such as I think Bill mentioned earlier in the middle of the talk, can we say something probabilistic about the outcome of a computation? So perhaps that can be given in a type setting. And then similarly, we have been thinking about resource theories. So we had a draft earlier in last year where we can say more abstract things about certain entangled states based on some sort of resource monotones, such as which specify how much entanglement exists in a certain state. So that lets us avoid going into the simulation trap. One direction, obviously, is can we reason about a large algorithm, such as Shor's factorial algorithm, by symbolically over parameterized over certain qubits n. So that will be that will make this technique very useful if it does not suffer through scalability challenges. And like we alluded to in the last slide, I mean, this work did, as Bill mentioned, only deal with pure state. So can we avoid the trap of simulation or using density matrices to reason about quantum computation? And like how far can this, using ghost variables to track amplitudes, I mean, this approach can take us? I think it's an open question and it will be interesting to find out. And with that, let me conclude, and thank you so much. I would be happy to take questions, and here are some collaborators who have helped me think through some of these ideas, and some papers that I did not mention, but I've greatly benefited from some of these are books as well. Thank you so much. I'll stop the recording unless there are questions. Maybe I should wait for that.
Yeah, I could ask something. So you've sort of truncated in a way Dominic Unru's work, logical system. So I'm wondering, what do you think that you've lost by doing so in terms of expressivity? And also sort of do the laws. I note that Unru often sort of shows some derived rules that are simplified versions of the rules that are in his logics. Can you find equivalents of your rules inside, or at least change from QHTT to QHL inside Unru's own?
Yeah, that's a good question, because I think the reason I'm able to get away without using all of his rules is because of the use of, basic Hoare-logic style rules that Hoare type theory provides us. So we have basically taken their, rules for consequence and composition as they stand and just replaced the primitive commands and state modeling there. So a lot of these rules that Unru shows us are for composing things together that HTT is already giving us. So that is part of it. And I believe some of his other rules may become important to us when we start looking at more examples. So I think that's currently a limitation of what I've done so far.
Mm-hmm.
Yeah.
I guess we should say thank you to the speaker and clap.
Thanks.